So today's lecture is lecture 14. It's about the Laplace transform. So one of the very important technique in all of mathematics, probably the Laplace transform. It gets widely used. There's a lot of applications related to the Laplace transform, especially in mathematics, physics, and engineering. And that's the focus of today's lecture and also for the next few days of our class. And the focus is on understanding the definitions of Laplace transform. How would you do Laplace transform on some very common functions like constant function, exponential functions, trigonometric function, more specifically sine, cosine functions. And we talk about signals and how would you transform or understand the signal that you get by doing the Laplace transform on piecewise defined function. Because for signal, we don't usually have continuous signal at all time from negative infinity to positive infinity, but we do have continuous signals on certain time interval. Right? Because of that, we can define those type of signals as piecewise defined functions, and we can do a Laplace transform on that. And hopefully today or on Wednesday, we're going to focus on solving the initial value problem just like we did before, but using Laplace transform and the inverse Laplace transform. So that is a brand new process, brand new solutions method that is very powerful. Before going to what is the Laplace transform, I want to bring up some of the definitions. All right, so what is transform, right? So we talk about Laplace transform, but in general, what is transform? So in what we are focused for our class is that the transform is the process of mapping mathematical functions from one domain to another. Well, in a way, we change the perspective of the functions. Right? So for example, this is the signal from the humpback whale that they collect. This is from, so they call it the time domain, right? So this is the signal that they got. And what they do is that they want to analyze this information. What should they do? So they change the perspective. Instead of the information from the time domain, right? So this is the x-axis is for time, the y-axis is the information that they get. So this is y of t. Now they transform to something else. So this is called the frequency domain, where you have different peak stand for different frequencies. So the x-axis here is for frequencies, and the y-axis is the information that you want to analyze. So doing this instead of something like a lot of noises, right? You can isolate different noises, different information based on the frequency, and then you can just get rid of all the noise that do not depend on the well, the noise of the well, and then analyze the humpback whale song. Right? So that is one way to look at this. That is the process of transform. Now, why use transform? Right? Some mathematical problems are very difficult to solve using their natural domain. Right? As you can see in the past few days, when we talk about solving the second order differential equations, we have to very specifically use the solution technique for very specific functions. That is, for sine and cosine functions, then it's okay to use undetermined coefficients. But if you have the forcing term to be, let's say, tangent function or cotangent functions, then it's become more challenging to use undetermined coefficients. Then we have to switch to variations of parameters. Okay, and so in a way, we have been doing transform already. We transform the second order differential equations to characteristic equations. We transform the forcing term to particular solutions, right? And doing that, we can find the solutions based on the very specific functions or differential equations. Okay, now what we're trying to do in this lecture is, or in the next lecture, is to solve for or build a solution technique where you can solve for the differential equation without thinking about what type of functions that we have to use to that fit into a certain solution technique. Okay, so you want transform to and solve in a new domain where the problem is simplified, right? And transform what you get in the new domain back to the original domain. Right? So you transform the differential equations to an algebraic equations, and then the trade-off, however, there's the trade-off, right? The trade-off is that you have to spend an extra effort on transforming and the inverse transforming for simplifications to the solution procedure. You will see, right? So the main point is that, okay, give me any differential equation, I can use Laplace transform. Give me any forcing term, I can use Laplace transform to find the solutions. Okay. And again, I want to bring up the applications of Laplace transform and inverse Laplace transform. Not only the example that we had earlier here on the signal that you got from the humpback whale song, but also in reality when the voice whatever I'm saying here, you have the signal, right? Your ear pick up the signal, pick up the voice that I have, pick up the noise that I make, right? And the ear can analyze the voids and then give you the information that you need to hear. Or when you play the song is a composition of a lot of noises, a lot of signals, right? Including the voice of the singer, the noise or the signal from the guitar, signal from the piano, signal from violin. Let's say those signals individually give you a sinusoidal waves, right? So like this. Okay, but when they get put together, this is the type of signal that you're going to get, right? So this is individual sines. This is the sum of all the sine functions. And when you receive something like this, it's very hard to analyze which one is for the guitar, which one is from the voice of the singer, which one is actually from the noises made by the audience, right? Something like that. So using Laplace transform, or in general case, if you in science, math, computer science, physics, and engineering in general, you will hear this term like Fourier transform, and they can analyze this information and pick out the frequency for the guitar, frequency for the piano, or frequencies for the voice of the singer. Okay, so it's very important to know how to do this type of a problem is a very practical way to learn mathematics. Another applications I want to give you is that there's a lot of applications that you can use to analyze information in medical field. Right? So this is the biosignal that you get when you use the ECG or EKG measurement. Okay, the ECG is the electrocardiogram. Okay. So it's one of the most used biomedical signal for diagnosis cardiovascular diseases, right? And if you just read this information, you cannot really analyze anything, really. But what you can do is that you use Laplace transform to analyze this information and transform the signal in time domain to a signal in frequency domain, where you can detect any abnormal activity in the heart. Okay, so this is the detection of extracytosis that a doctor can pick up, and that can help you analyze the information and give you the diagnosis if you have any heart disease or not. Right? Because the information you get here consists of a lot of information, right? Including what you see that about the mental stress, about the blood loss, about the medications that you're using, and about the illness that you experience. Right? A lot of noises in this picture. However, if you transform that to a frequency domain, then this is the normal heart behavior, right? Or the normal heart signal, but this is the abnormal signals that you can pick up, and from there you can give the patients the diagnosis that they need. So I want to bring up just a very few examples related to Laplace transform or integral transform in general. In practice, there are many more applications that you can use with Laplace transform. I cannot stress enough how much Laplace transform get used in the workplace in reality. If you take differential equations, you learn a lot of topics, and the one topic that I want you to take home is the Laplace transform. How useful the technique is and how important that is in reality. Okay. So that's just some motivations for you to jump into Laplace transform. But yes, there's the practice that you can do, but what we need to know is how to actually carry out the calculations and understand how it get used in certain examples. The Laplace transform is actually fall into a particular procedure is called the integral transforms. So an integral transform is the relations of the form. You have capital S equal to the definite integral from alpha to beta of k of s comma t times f of t dt. All right. Where k st is called the kernel or a given function. Alright, so for this kernel, for this given function, it depends on the integral transform, then you have a different kernel. For the Laplace transform, the kernel that we're going to see is the exponential functions, the real exponential functions. For another type of integral transform is called Fourier transform, is a complex exponential functions. You have another transform is called Hankel transform. So they have different type of integral transform, and with different integral transform, you have different kernel or different k of st. Alpha and beta are limit of integrations. And capital F is the transform of little f. So little f can be a forcing term, right? Can be anything, can be a sine function, can be a cosine function, can be another exponential functions, can be, you know, a constant function, whatever that is. Okay. And this is in general, this is the formula for the integral transform. And again, for Laplace transform, you will have an exponential function in the place of the kernel. So definition, Laplace transform of the function f is of the form. Right, so I'm going to use fancy L here to stand for Laplace transform, but certainly you can use just the capital L stand for Laplace transform. But I'm going to use a fancy L here to write my Laplace transform. So is L, and Laplace transform is an operator. You apply this operator on a function f. So I use this notation. And this is equal to the infinite integral from 0 to positive infinity of f of t times e to the negative st dt, provided that the improper integral converges. So this is a kind of illustrations to understand the Laplace transform. Right. So you receive a lot of signals. So this is the signal, and combination of the signals give you this information in the time domain. Okay. So as you can see, there's a lot of noises in there. Now what you do is that you transform this information in the time domain to the frequency domain, the informations that you got in the frequency domain. Let's say this is the main signal that you want to pick up. This is the noise that get blended in the informations, right? So if you pick out this type of noise using the frequency domain, you can get rid of this and then just analyze the main informations that you need to analyze. Okay, so that's basically the procedure. But in practice, of course, there's a lot of finer details that you can follow in order to go from the differential equations that you got to the solutions that you need. Okay, so technically in mathematics, in physics and computer science, or in general, what you have usually is the differential equations, right? So you start with differential equations. You get the informations about the first derivative, second derivative, third derivative, so on and so forth. Depends on the differential equations that you're working with. You can have functions of, let's say, just y double prime, which is the second order differential equations. But certainly for Laplace transform, you can do the differential equation, the third order differential equation, or the fourth order differential equation. But let's start with just the second order differential equations. Okay. And then from the differential equation, you're going to use Laplace transform to turn this information of differential equation in the time domain to the functions, let's say capital f of s, in the frequency domain. And this is the time domain, and you Laplace transform. So you use Laplace transform to transform the differential equations to functions in the frequency domain. Usually the differential equations will be turned to an algebraic equations in the frequency domain. You will see it later. And then when you analyze the information that you get in the frequency domain, then you need to transform the information that you got in the frequency domain back to the original domain or back to the time domain. And to do that, you have something called the inverse Laplace transform. Okay, and you get the informations of y of t, and y of t is the informations that you need. Solutions in time domain. Okay. So that's the procedure. What we are the focus for today's lecture is just the Laplace transform. The next lecture is on the inverse Laplace transform. So I break it down into two different lectures. So go back to the definitions of Laplace transform. You can see this is the improper integral or infinite integral. So you need to apply this type of integral in finding the Laplace transform of the functions. So let's start with easy one here. Let's say find the Laplace transform of just 1. Right? So in other words, find the Laplace transform of the function f of t equal to 1 and assume that time is greater than 0. So because we usually work with a time domain, therefore we consider the time to be a positive variable. Okay, so Laplace transform of 1 is going to be, so I have Laplace transform apply on 1 is equal to the improper integral from 0 to positive infinity of the kernel here, which is e to the st, times 1 dt. Okay. So 1 is the function that we need to apply Laplace transform on. E to the st is the kernel. This is specifically for the Laplace transform. Okay. So because this is the improper integral, you need to apply limits as n go to infinity. And then you turn this improper integral to limit of definite integral. It's from 0 to n of e to the negative st dt. And then at this point, you find the antiderivative of e to the negative st. This gives you limit as n go to infinity of negative 1 over s times e to the negative st, evaluate at 0 and capital N. And then I still have limits as n go to infinity of negative 1 over s. And when I do substitutions, I get e to the negative sn minus e to the 0. So e to the 0 is going to be 1. So limits as n go to infinity of negative 1 over s times e to the negative sn minus 1. So negative 1 over s, for s is just a constant, you can pull negative 1 over s out of the limit operations. And then limit of a difference is difference of limit. So the limit of this exponential functions as n go to infinity is going to be 0. Okay. So you only need to have negative 1 over s, then limit e to the negative sn as n go to infinity, minus the limit of negative 1. Right? It's just a constant, so it's just minus 1 here. And this will go to 0. Right? So because the exponential function is decaying or going down or decreasing and approaching 0 as n going to infinity. Now that is negative 1 over s times negative 1, and you just have positive 1 over s. So Laplace transform of 1 is 1 over s, given that s is greater than 0. Alright, so I'm going to give you another example on how to apply Laplace transform in finding Laplace transform of some common functions. The next one is you apply Laplace transform on an exponential function. Not only that, I have a question here that is, what is the value of s in this problem? So quite specific. It's not going to be not only greater than 0, but actually greater than something. So Laplace transform of the function e to the at for a is a constant. Now you have the improper integral from 0 to positive infinity of e to the negative st. This is the kernel, this is the specific function for Laplace transform. You multiply that with the function e to the at. This is the function we need to do transform on. All right. Similar to the previous example, we're going to turn this improper integral to limit of definite integral. So you have limit as n go to infinity of the definite integral from 0 to n of e to the, so I combined the exponent together, right? They have this, we have the same base here, combine the exponent together. So e to the negative st plus at dt, and this is equal to limit as n go to infinity of the definite integral from 0 to n. Okay, so of course, eventually I want to find the antiderivative of this function. So what I do is that I take, let's say I take negative t as a common factor. You will see in a minute why that is the case. So I take negative t as the common factor, and I left with negative of s minus a altogether times t dt. Then I find the antiderivative of this function, and again limit as n go to infinity of negative 1 over s minus a times e to the negative s, so negative s minus a times t, evaluate at 0 and n. And then you do substitutions here, or evaluate the function at 0 and n. Here's what you got, limit as n go to infinity of negative 1 over s minus a, and you have e to the negative s minus a times n minus e to the 0. So as before, negative 1 over s minus a is a constant, so you can pull that out of the limit operations. Then apply the limit on the difference here. Limit of a difference is difference of limits. So that's what you get. So negative 1 over s minus a times the limits of e to the negative s minus a times n as n go to infinity. And then limit of e to the 0, e to the 0 is 1, limit of 1 is just 1, so you subtract 1 here. Okay. So now you apply the limit of this function, and look very similar to what we see up here, right? We show that s is a positive number, n is positive because n go to infinity. So this is a decreasing function, right? Decreasing to 0 as n go to infinity. You want to have something like this, like that, for our analysis on this term. So what we do is that we let n go to infinity, right? And you want this exponential function to go to 0. The only case that can happen is when s minus a is a positive number, or s minus a is greater than 0. If s minus a is less than 0, then you have an increasing exponential functions. Then this limit go to infinity, positive infinity, and you don't want that to happen. So the conditions that you need to impose here is that s minus a is greater than 0, right? So positive times positive is positive, times negative is negative. And because of that, when you apply limits as n go to infinity for this function, the function tends to 0. Okay, so this go to 0 under the assumptions that s minus a is greater than 0. Okay. And because that function go to 0, that limit go to 0, you get negative 1 over s minus a times negative 1, and that's give you 1 over s minus a, so that is the Laplace transform of e to the at. Okay, and under the assumptions that s greater than a. So be careful when you do the Laplace transform. There's certain conditions that follow with the Laplace transform. For the first problem, Laplace transform of a constant 1 is 1 over s, given that s is greater than 0. Here, Laplace transform of e to the at is equal to 1 over s minus a, given that the value of s has to be greater than a. Okay. So that's another Laplace transform on exponential functions. I'm going to give you one more example on Laplace transform of some common functions. This takes a little bit longer to do, and after this example, I will introduce to you the Laplace transform table, where you don't have to do Laplace transform by hand anymore. I just want you to see Laplace transform in actions, how it can be done, what formula that we use, and how we can use the knowledge that we have in calculus 1, calculus 2, and apply here to find Laplace transform of some functions. Okay, So Laplace transform of psi of at. So this is the Laplace transform of psi function. You can do the same thing for Laplace transform of cosine functions. So Laplace transform of psi of at is equal to the improper integral from 0 to positive infinity of e to the negative st times psi of at dt. Okay. And again, you turn this into the limit of definite integral. You get limit as n go to infinity of definite integral from 0 to n of e to the negative st times psi of at dt. So you have a product of exponential function and trigonometric function. What you do is you use integration by parts, right? So you integration by parts to evaluate the integral. So that is what you do is you let u equal to psi of at. Therefore, the u is equal to a times cosine of at dt, and dv is equal to e to the negative st, or v is equal to negative 1 over s times e to the negative st. Okay. Now for integration by parts, just want to remind you this type of functions, right? This is the product between exponential function and sine or cosine functions. So when you encounter this case, you can either use u equal to psi of at or u equal to an exponential function. It does not matter. When you encounter this problem, you have to do integration by parts twice in order to get the answer. And when you do it twice, if the first time you let u equal to trigonometric functions, then the second time you have to let u equal to another trigonometric functions. If the first time you use u to be an exponential function, then the second time you apply integration by parts, you have to let u equal to an exponential function as well. So be careful on that. So this is the first integration by parts. Substitute this into our calculations you get. So this gives you limit as n go to infinity of, so u times v minus v du. So u times v is 1 over s times e to the negative st times psi of at, evaluate at 0 and n, minus v du, but there's another negative here, so you have plus 1 over s times the integral from 0 to n of e to the negative st times cosine of at. So there's an a here as well, so I pulled that out of the integral operations. So instead of 1 over s, I have a over s. Okay, so apply another integration by part on this integral. You let u equal to trigonometric function again, right? Because the first time you do integration by part, you let u equal to psi of at. Then the second time, you let u equal to cosine of at, or du is equal to negative a times psi of at dt, dv equal to e to the negative st dt, or v is equal to negative 1 over s times e to the negative st. Then the Laplace transform now become limits as n go to infinity of negative 1 over s times e to the negative st times psi of at, evaluate at 0 and n. So I just bring this term down. There's nothing changed there. Now for this integral, I have a over s times u times v, so negative 1 over s e to the negative st times cosine of at, evaluate at a, n, and 0, minus a over s, so minus v du, 1 negative, 2 negative, and then another negative, so that's why you have negative a over s, times the definite integral from 0 to n of e to the negative st times psi of at dt. So that's what you get. So it looks like we are going in a circle now, because you start out with the integral from we start out with the integral of e to the negative st times psi of at, and at this point we also have the integral of e to the negative st times psi of at. So what you do is that you let the left-hand side to be equal to a number, right? So to, let's say, a variable capital F, and here you also let that to be a capital F, and then you combine like terms together and solve for that variable that you just replace. Okay. So on the left-hand side, let me, instead of writing Laplace transform of psi of at, you're going to replace that with, let's say, capital F of s. Okay. Well, basically this one is capital F of s. Okay. That is the left-hand side. So the left-hand side is capital F of s. Now on the right-hand side, you apply limits. Right? So limit of this term, limits as n go to infinity of -1 over s times e to the negative st times psi of at, evaluate at 0 and n, plus limits. So be careful with me. So be careful here. You distribute a to the s, right? Sorry, a over s. You distribute a over s. You have the limits as n go to infinity of -a over s squared times e to the negative st times cosine of at, evaluate at 0 and n. Then you distribute a over s to this term. You get limit as n go to infinity of -a squared over s squared times the definite integral from 0 to n of e to the negative st times psi of at dt. Alright, so that's it, man. It's a lot to keep track of. Now, when you take -a squared over s squared out of the limit operations, and you only have limit as n go to infinity of this integral, that's technically capital F of s. Alright, so instead of just doing the calculation, what you do is you do the replacement, or you do the substitutions, right? So now you have -a squared over s squared times capital F of s, and that is what you're looking for, capital F of s. So let me do that. Capital F of s on the left-hand side. You have a bunch of limits here. -1 over s times e to the negative st times psi of at, evaluate at 0 and n, plus another limit as n go to infinity of -a over s squared times e to the negative st times cosine of at, evaluate at 0 and n, minus a squared over s squared. Now, again, the limit of this integral is actually capital F of s, so you combine that together with the one on the left-hand side. So you move this term to the left-hand side, and you get capital F of s plus a squared over s squared times capital F of s. Now, the remaining terms on the right-hand side, you still need to evaluate, right? You have to evaluate the function as n and 0, and then take the limits of that and see what happens. Alright, so you have this one, limit as n go to infinity of -1 over s times e to the negative sn times psi of an minus e to the 0 times psi of 0. Okay, so psi of 0 is going to be 0 anyway, so eventually this will go away. Plus another limit as n go to infinity times -a over s times e to the negative sn times cosine of sn minus e to the 0 times cosine of 0. Okay, so close the parentheses here. So now work with me here. E to the 0 times psi of 0 is 0, so this term is 0. You see this this analysis earlier already as n go to infinity, and we make the assumptions that s is greater than 0, then this term will go away, right? So as you apply limit, so this one go away. So technically, this whole thing is 0. Similarly, when you apply limit as n go to infinity, and under the assumptions that s is greater than 0, this term will go to 0 as well. Now we have the last term here. Either the 0 is 1, cosine of 0 is 1 as well. So you have 1 for this, for the calculations. All right, so a lot of terms get dropped out of the calculations. Now what you do is you still want to calculate capital F of S. So take capital F of S as a common factor. You're left with 1 plus a squared over s squared equal to the right-hand side. Now the right-hand side is only negative a over s times negative 1. So the negative 1 coming from this negative sign here. Okay. So capital F of s times, you combine these two terms together, find the common denominator. That's give you s squared plus a squared divided by s squared. I make one small mistake here, that this term is negative a over s squared. When I rewrite this down here, I forgot the square. So negative a over s squared. And here as well, a over s squared. So the right-hand side give me positive a over s squared. So s squared is the common terms on both sides of this equation under the assumptions that s is greater than 0. You can get rid of it. So capital F of s times s squared plus a squared equal to a. And therefore, capital F of s is a over s squared plus a squared. And this is the Laplace transform of psi of at. Okay. Now, as you can see, there's a lot of work involved in finding the Laplace transform of some function, and this is just a very common function, so psi of at. And you will encounter something similar when you find the Laplace transform of cosine function. They have a very similar procedure, and the results are going to look similar as well. So Laplace transform of cosine functions is going to look like this: capital F of s equal to s over s squared plus a squared equal to Laplace transform of cosine of at. And you have to go through the whole procedure one more time. It's just too much time and effort, right? Ain't nobody got time for that, right? So therefore, what I'm doing is I'm going to show you a table of Laplace transform. And therefore, from now on, if I don't ask you to specifically calculate Laplace transform of some function, you can just refer that to Laplace transform table and you get the results, right? Alright, so you have 4 different columns in this table. Right? So this basically you can just Google it and you see this type of table. On the left hand side is the function, right? It's the function that you want to apply Laplace transform on. So let me go through a few of them here. So you have Laplace transform of an exponential function e to the at. Laplace transform of that is 1 over s minus a. That's what we did, right? You have Laplace transform, let's say, of a constant, right? Let's say the constant, where's the constant here? There's no constant that I see. Right, if a is equal to 0, right? So if for exponential function, if a is equal to 0, then you have the constant 1, and then you have 1 over s minus 0 technically, and then you get the answer. If you have a power of functions, t to the power n for n is 1, 2, 3, 4, so on and so forth, then the Laplace transform is n factorial over s to the power n plus 1. Okay, so you don't have to reproduce all of these calculations. Over here you have the Laplace transform of psi of bt or psi of at or psi of kt, doesn't matter which one. The Laplace transform of that is b over s squared plus b squared. Laplace transform of cosine functions. Okay, so this is the Laplace transform table, and this is some of the very common signals that you're going to pick up in analyzing the signal in reality. You have a lot of sine function, cosine function, exponential function, and constant functions. And again, you don't have to reproduce all of these calculations anymore. unless I specifically say so. Because eventually later on in the notes you will see the Laplace transform of some piecewise defined function usually is not going to be able to fall into one of this category. So you have to analyze or apply the definition of Laplace transform to find Laplace transform of some function like that. And then maybe on Wednesday, those piecewise defined function will get clumped into another category where you can look at the table and find the Laplace transform without doing the calculations. But that's for Wednesday. Okay. And if you start on this side, this column, the next column should be the Laplace transform. Okay, so this side or this column is the function, then the next one is the Laplace transform column. In the reverse directions, you will be able to find the inverse Laplace transform. Right? If you start with this column will give you the inverse Laplace transform. Similarly, if you start with this column will be the inverse Laplace transform. And that is for the next lecture. But for now, let me get back to our notes here, Laplace transform. So we're done with kind of finding the Laplace transform of some common function using the Laplace transform definition.